We begin our journey in chapter 15, which is going to discuss topics in vector calculus. And in section 15.1, we're going to introduce the notion of vector fields. So first, let's define what a vector field is. A vector field in a plane is a function that associates with each point in P a unique vector f of P parallel to the plane. So we're inputting a point P, we're outputting a vector at that point P. Similarly, a vector field in R3 is a function that associates with each point P in R3 a unique vector f of P. So very similar there in 2 dimensions. We have some notation here. It says in R2, f of P can be expressed in the IJK notation. So, and that's a typo there, should be in R3. So what we're seeing is we're inputting a point XYZ, and then we're outputting this vector where each coordinate in the I, J, and K coordinate is defined by a coordinate function. So let's work with some examples here in drawing some vector fields. First of all, 1A, we have f of xy is xi hat. Notice that this is independent of the y coordinate. The output only depends on the x coordinate. So let's sketch a quick graph here to show this vector field. I am going to sketch an xy coordinate axis. And then because this vector field is independent of y, what I'll do is I'll do sets of sets of points with the same x value all at once. So for example, let's consider any point that's of the form 0, comma y. And so those are going to be points that lie on the y-axis. You'll notice that the x coordinate is 0, so the vector that it's going to output is 0 I hat. In other words, we just get a point at each of those. I'm just assuming x is some integer value. All right, now let's look at the next set of points where the x coordinate is 1 and then y is anything. All right, so if x is 1, then what we're doing is we're outputting the coordinate I hat. So let's look at 1, 0. We're going to output a unit vector that's pointing in the I hat direction or towards the positive x-axis. And so on and so forth. And just draw enough of these vectors to convey what you're trying to say here. Let's also look at -1 x coordinates. So that's going to be very similar, but instead of an I hat, we're getting a negative I hat. So we're pointing in the opposite direction. Now, we could play this game for an eternity. We could plug in a bunch of different points, but what I'll do is I'll also just plug in, for example, 3y. So 1, 2, 3. And these are going to then output 3 I hat. So they are vectors of length 3 pointing in the positive I hat direction. And so what you can see is as we get further away from our y-axis, our vectors are lengthening. And in the positive direction, if we're on the right of the y-axis, and of course the negative direction, if we're in to the left of the y-axis. So I'll draw some of these -3 I hat vectors as well. All right, so the understanding is that this vector field goes on for eternity, both up above and below, but also side to side. So just use your judgment to draw enough vectors to illustrate what the vector field looks like. All right, so that's 1A. 2A is unique. What we're noticing is we're inputting a point xy and we're outputting I hat plus j hat. So this vector field is independent of both x and y. It doesn't matter what I plug in for this vector field. This is a constant vector field. So I could plug in 1, 1, and I get out I hat, j hat. I could plug in negative 2,000, positive 768, and I'm still getting out I hat plus j hat. So what does this vector field look like? All right, so here's my X and Y axis. And at any point in the world, I'm going over 1 on the X axis and up 1 on the Y axis. And here is my I hat, J hat vector. Now I drew this vector emanating from 0, 0, but of course we have these vectors everywhere in the plane. So I'll draw one all along the X axis. I have them all along the Y axis. And I have them everywhere in between. These should all be the same length, and they should all have the same slope, angling up at a 45-degree angle. Okay, so here are two examples of drawing a vector field. Now, in my course, I disallow calculators, which means if I'm going to ask you to draw a vector field, I'm not going to ask you to draw anything crazy. I'm not going to have, for example, f of xy equals sine of x I hat plus cosine of y j hat, because it's too hard to evaluate those without a calculator. So what I'm going to expect of my students is to be able to draw very simple vector fields by hand, and then we won't stray into any super exotic vector fields if we're sketching them by hand. All right, so next what we want to do is we want to introduce what's called the gradient field. This should look very familiar to what we have discussed before. So the gradient field is a vector field that inputs a function and outputs a vector whose coordinate functions are just the partial derivatives of that function in each variable. And so I just made a note here that I have it defined in 3 dimensions, but you can just as well define it in 2 dimensions. All right, so again, what I want to recall here is that the gradient inputs a function. This is a real valued function. And it's outputting a vector, right? The partial with respect to x, the partial with respect to y, and the partial with respect to z. This is a vector. I always want you to stop and reflect as to what world you're living in. Are you in the world of scalars or are you in the world of vectors? Now, very similar, but yet distinctly different from the gradient field is what we'll call the divergence. We're now looking at a vector valued function f. So I'll just note here, vector valued function, as opposed to the gradient up above where we had a real valued function. And then we're going to define the divergence of f. So that's written with this div f, div in front. And that is the function that's given by the partial of the x component function, which we've called f with respect to x, plus the partial of the g component function with respect to y, and the partial of the h component function with respect to z. So what is this? This is a scalar. All right, so the gradient inputs a real valued function, outputs a vector. The divergence as an operator inputs a vector valued function and outputs a scalar. I see these two confused on the final exam quite often, so make sure you recognize the difference between the two. All right, so let's do an example here of divergence. I want to find the divergence of f, and I'm going to emphasize that that f is a vector valued function by putting a vector hat on top. So the first summand is the partial of the first component function with respect to x, which is going to give me a z cubed, plus the partial of the second component function with respect to y, which is an 8y cubed x squared. And the final summand is the partial of the last component function with respect to z, which is a 10zy. And so this expression right here is the divergence of the vector valued function f. Similar to divergence, we can also define the curl of a vector valued function. So here f is always bolded because that means it's a vector valued function. And what the curl is the determinant of the 3 by 3 matrix composed of the unit vectors I, j, k, the partials with respect to x, y, and z, and then those three component functions f, g, and h. So, on a personal note here, I do not have this memorized. All that there is that I highlighted there in red is just the definition of a determinant of a 3 by 3 matrix. So, what I do is I just remember what the curl is defined to be in terms of the determinant of that matrix, and then I compute it accordingly. I am never running through this red portion of the equation. All right, so we want to look at that exact same vector valued function in 18 and now compute the curl. So what I'm going to do is I'm going to set up my matrix first. So I always have I, j, and k across the first row, and I always have partial with respect to x, y, and z across the middle row. Those two rows never change. It's independent of your vector valued function. And then the bottom row is specific of your vector valued function. So we have the first component function, xz cubed, the second component function, 2y to the fourth x squared, and then the third component function, 5z squared y. And now I'm going to carry out this determinant. So let's do the I hat component first. So if I strike through the I hat column and row, then what I'm going to do is I'm going to take the determinant here. So I'm going to go across the main diagonal. So the partial with respect to y of 5z squared y is 5z squared. And then I want to subtract off the partial with respect to z of 2y to the fourth x squared, which is 0. And now I'm going to move on to my next component function, which is always negative. So I'm noting that negative there so that I don't forget. All right, so now let's strike through the j hat row and column. And I'm going to take the determinant of that cofactor matrix. So across the main diagonal, the partial with respect to x of 5z squared y is 0, minus the partial with respect to z of xz cubed is a 3xz squared. And finally, I have my k hat component. So let's find that one. I am going to strike through the k hat row and column and compute the determinant of its cofactors. So the partial with respect to x of 2y to the fourth x squared is 4y to the fourth x. And then the partial with respect to y of xz cubed is 0. So what I get here in the end, dropping all of those unnecessary zeros, is 5z squared. Double negative makes a positive 3xz squared, and a 4y to the fourth x. And so this vector is the curl of f. So again, one more time, the divergence is a scalar. That up there is just an expression. The curl is a vector. All right, so I'm just highlighting here again, divergence is scalar, curl is vector. Make sure you use the appropriate notation. For vectors, the angle bracket notation is fine, or also the IJK notation is fine. So let's do one more example of computing divergence and curl. So let's start with divergence. It's quicker to compute. All right, so for the divergence, I want to take the partial with respect to x of my first component function. The chain rule is going to kick out a y, and then I have my e to the xy. Then I always add the partial of the second component function with respect to y. Negative cosine becomes a positive sign. And then finally, if you want, you can rewrite that last component function as a sine z quantity squared. And so I'm going to use a chain rule here to take the partial with respect to z. That is a 2 sine z cosine z. Whoops. And no simplification required for the divergence. Next, let's compute the curl. Again, always filling in I hat, J hat, K hat, partial partial X, partial partial Y, partial partial Z. Those are fixed every single time. And now I'm going to plug in my component functions, e to the xy, negative cosine y, and sine squared z. And let's compute what this curl is going to be. So going through again, I'm going to strike through the I hat row and column. And you'll notice that in this first diagonal is 0 because there are no y terms in sine squared z. And the second term is also 0 because I don't have any z's in negative cosine y. So that results in 0 for our first component. So now let's strike through the j hat row and column. Again, we're getting a 0 minus 0 because our partials are not matching up with the variables in our component functions. And finally, let's strike through the k hat row and column. I get nothing for my first diagonal, but there is finally something in that second diagonal. So when I take the partial with respect to y of e to the xy, the chain rule is going to kick out an x, e to the xy. All right, so for my curl, my final answer is 0, 0, and negative x e to the xy. All right, so there you can see the difference between the divergence and curl. So you'll notice throughout here that we're working a lot with these partial derivatives as operators. In certain areas, we're taking partials with respect to x and others with respect to y and z. And so that brings us to the del operator. The del operator is defined to be the operator that's going to output the partial x in the I hat component, partial with respect to y in the j hat, and partial with respect to z in the k hat. And so we're used to this operation because we're used to thinking about the gradient, right? And so we talk about the gradient being the partial with respect to x of our f function and so on and so forth in each coordinate. So this isn't so much new notation, it's just that we've never used the term del operator. So using this del notation, we can now express the divergence as del dot f and curl as del cross f. I really, really like this notation because hopefully everybody feels confident in the fact that the dot product outputs a scalar and that the cross product outputs a vector. And so if you can remember this notation that the divergence is del dot f and that the curl is del cross f, then that'll help you remember whether you're living in the world of scalars or vectors. We can build upon the del operator if we act it on itself via the dot product. So del dot del, which is also denoted as del squared here, is the Laplacian operator. And you can see what it is. Again, we're working with a dot product, and so that's going to output a scalar. And it's just the second partial with respect to x plus the second partial with respect to y plus the second partial with respect to z. So that is the Laplacian. To round out this section, we just have a couple more examples here that's just working with that del operator and making sure you feel comfortable working with not only the del operator, but also dot and cross products. So in 24, we want to find del dot f cross g. Make sure you're working with your order of operations. You have a couple of options here. You can either carry out the cross product first and then dot with the del operator, or you can recognize that this is just a scalar triple product. And so we saw this way back in chapter 11, that we can carry this out in one fell swoop if we just set it up as the determinant of a 3x3 matrix. And so what I'm going to do is I'm going to say, all right, look, if I want to do this all at once, del dot f cross g just is the determinant of the del operator across the top, which is del del x, del del y, del del z. And then the next two rows are the component functions of f and g. So I have yz, xz, xy, and then I have 0 in the I hat component of g, xy, and xyz. All right, and so let's carry this out. I'm going to actually be really careful about writing this out. So I'm going to write this as, first I'm going to strike through the del x row and column. And so I'm going to write that del x notation. And then I'm going to take the determinant of the cofactor matrix. So I get an x squared yz squared minus an x squared y squared. And now I'm going to move on to the next term. If I expand across the top row, I have the del y. Now remember, when you're computing determinants, you always switch signs. So this is del y. And now taking the determinant of this cofactor matrix, I get x y squared z squared minus 0. And then finally, I'm going to move on to the last term. And I'll just strike through the del z column. And that is going to give me x y squared z minus 0. And so now let me carry out the partial derivatives. This is going to be a 2xyz squared minus 2xy squared. Moving on to the next term, minus 2xyz squared. And then finally, an xy squared. And so let's see if we can combine any like terms. It looks like these two terms are going to cancel, and I can add the remaining two terms. And so I end up with a negative xy squared. All right, so that is del dot f cross g. 26 is a similar problem. Here we're doing del dot del cross f. So I'm going to continue on with the same approach where I'm just going to do the scalar triple product in one fell swoop. I want del dot del cross f. So my first and second rows are going to be the partials in each coordinate. I'm going to recopy that here in row 2. And then I'm just going to add in the component functions for f across the bottom row. So e to the xz, 3x e to the y, and negative e to the yz. All right, so just like what we did in 24, I am going to carefully write out each of these so that I don't try to do everything all at once and make a mistake. So let's strike through the first row and first column. And so that's going to give me, if I take the partial of negative e to the yz with respect to y, I'm going to kick out a z. And then minus 0, since there are no z's in the other term. Now let's strike through the next column. So I'm going to take now minus partial y of. All right, let's compute the determinant. I get 0 minus x e to the xz. And finally, plus partial z of. Strike through the appropriate column here. And what I'm getting is 3e to the y minus 0. All right, so now we're ready to take these final partial derivatives. Partial with respect to x is 0. Partial with respect to y is 0. Partial with respect to z is 0. So in the end here, del dot del cross f was just equal to 0. All right, and that's all for this lesson.